ECE faculty actually in his space. Okay.
All right. How long do I have? It's 9:10.
So you have 15 to 20 minutes.
Okay, just so I have a clear target. Welcome everybody to BU. My name is Milos Popovic. I will introduce you to one of the three areas of research in electrical engineering, the electrophysics branch of the department. And you hear me on the microphone? Okay. Welcome also to everybody online. There's about another 10 people dialing in from various parts of the world. So let me just jump right in. So these are the electrophysics faculty. So you've got a lot to choose from. I'll give you a quick run through of the areas of research in electrical, and so we're just going to do a quick tour, give you a rough idea of what's going on, and then we can have questions if needed. So not everyone here is in the electrical engineering department. For example, well, Dave Bishop is appointed in electrical engineering, but he's actually the chair of the materials program. Then Xin Zhang is in mechanical engineering. Alex Sushkov is in the physics department, but he's cross-appointed in electrical and so on. Okay, so you're here. As Tom already said, the top half of the physical photonics center contains the labs that are part of the photonics center, and then the bottom half is the electrical engineering department, roughly. So these are approximately the areas of research that you will see. So it goes from biophotonics, computational electromagnetics and computational physics, applied electromagnetics and energy, laser science, nonlinear optics and ultrafast optics, fiber guided wave, integrated photonics, silicon photonics. Then a lot of work on materials and devices, optoelectronic materials, nanotechnology, nanophotonics, plasmonics and metamaterials, imaging, microscopy, spectroscopy, quantum optics and space science. So that's kind of how I divide it up. So my goal is to give you a little bit of a tour. Biophotonics, we have Li Tian. He's a new faculty member this is his second year here, and he works in an area called computational imaging. It's a very hot area these days. It combines optics and signal processing as two sort of equal contributors. And so, for example, your eye has a lens, a camera, every camera has a lens, but he works with some cameras that have no lens, or some microscopes that have no lens, or have some weird lenses that give you, for example, three-dimensional information, or can remove or let's say change the focus of an image after you've already taken the image and so on. And so many applications, a lot of them have to do with biology, because microscopy is a very important area, but also others. And so they combine work between optics and designing algorithms and coding and that kind of thing. Professor Selim Unlu works on all kinds of things, and he used to work more on chip technology nowadays. So one of his projects was optical detection of viruses. So there's an article here on detecting Ebola using optics. And Professor Irving Biggio works on, I guess my picture's over this, but cancer detection and also also activation of neurons and so on. This is one of his book on biomedical optics, just came out last year. Professor Chen Yang is also new to the department, so we've actually added about 5, 6, 7 faculty in the last few years. It's rapidly 7 faculty, thank you. She comes from Purdue University, and her work is in nanotechnology, so I guess related to biophotonics. She has some projects relating to biomaterials that modulate neuronal activity. This is a picture of silicon nanowires in cells and trying to figure out how they can be incorporated. And Professor Jijin Cheng is also, so this is, I guess, number 5 in biophotonics, according to my count. He has a lab of about 20 people, so he takes up about half of the building, doing all kinds of things. One of them is label-free spectroscopic imaging. So, and it's one of these from Maxwell's equations to the clinic labs. So they developed the technology for microscopy. So this is just a picture I captured of one of the microscopes. So you have a short pulse laser that then is used to capture a spectrum, all the way to applications. So this, for example, is a picture of a neuron stimulation. And let's see, move on to the next area. Computational engineering, electromagnetics, as well as physics. We have Enrico Bellotti, who's one of the world's experts in photodetectors. He has, I think, a $12 million center from a few years ago in this area, and they go all the way from Schrodinger's equation to designing devices and testing them. Professor Sahar Sharifzadeh is a computational material scientist. So she takes density functional theory. Most of her work is theoretical, or all of it, and she works on discovery of new materials. So I think one of our visitors here, Georgia, did undergrad research in that kind of stuff, right? She basically will try to discover new materials based on first principles computations using quantum mechanics. And so you might want, for example, I work in integrated photonics. I want an electro-optic material with a huge electro-optic coefficient. So her problem is, starting from first principles, can you give me something that doesn't exist in nature but that does better than any other material you can get? Robert Kotyuga is an expert in numerical methods. He did some seminal work in actually what now are finite element methods that you've all heard about. And a bunch of the rest of us also work in computational electromagnetics as part of our research. Then applied electromagnetics and energy. Professor Yang also works on nanostructures for solar energy applications. Then Minchang Li is our expert in electromagnetics, and he spends a lot of his time in Puerto Rico doing plasma experiments and trying to figure out properties of the ionosphere, for example, relating to pollutants or relating to the solar wind and so on. Mazumder and Horenstein have very sustainable energy projects to do with, for example, self-cleaning solar cells and so on. Then my next area, fiber and guided wave optics, lasers and nonlinear optics, I kind of put them together. Professor Siddharth Ramachandran is our fiber expert. So he mostly these days works with orbital angular momentum, with fancy modes in optical fibers for optical communications, for bioimaging applications, for quantum optics applications. So in this case, I guess this was an article on very high data rate transmission, and he was the general chair of the CLIO conference, which is one of the 2 major conferences in optics last year. Michele Sander is our expert on ultrafast lasers. So she goes from the technology of building new kinds of lasers, for example, in the terahertz, in the mid-infrared regime of a couple of microns to 10 microns, where it's very difficult to build lasers, to applications of lasers in imaging and spectroscopy, for example, here in nerve stimulation. Then we have a few groups working in nonlinear optics and ultrafast optics, silicon photonics, and materials and devices. That would be me. I work in integrated optics, so silicon photonics. We try in my group to design for first principles new devices that you can build on a silicon chip integrated with electronic transistors that serve new functions like CPU to memory interconnects using light, or new types of signal processing or computation like neuromorphic computing using optical signals. But we like to do things like build optical phased arrays, for example, for beam steering, or ask questions like, what's the most efficient you can make an optical modulator? Can you zero in on a couple that, one, you're interested in, two, are interested in you, three, are actually going to have dollars to support you, right? And then I think the plan is you see if you can sit in on group meetings. They might take you on for a rotation, something like this. And a week is, like you mentioned, is probably too short, but it's more like half a semester or like a third of a semester, so you can get an idea of what's going on.
And I know that would be difficult for you as well to find 3-4 week projects.
Right. Yeah. So I think. Yeah, right.
Just the only thing I said was that logistically that's difficult for the professors as well, finding small projects that can be done in a fraction of a semester.
And I think that depends on the situation. If you want to see what it's like in the lab, you can maybe you just see whether you can hang out in my lab for a few weeks and check it out. If, on the other hand, I'm concerned about whether your programming skills that you said, fit what we need or something like this, then it might need to be a little longer project so you can try it out and I can see how you're doing with that, how you're coping with that.
This is a really key question and super important. And I think during my presentation, we can talk more about that. And now we're sticking a little more to the subject areas. Since we have a schedule to follow, but thanks for a great question. Daniel, did you have a question? Okay. Then I think we will thank Milos.
Okay, thank you.
And I want to introduce Manuel Aguilar to you, who is a professor in computer engineering space. Let's see. Which one is it? CE.
So navigate with keys. All right. Hello, thank you, Anna, for the introduction. As the slides and the introduction says, my name is Manuel Aguilar. I'm an assistant professor in the computer engineering group here in the ECE department, and I'm very happy to tell you guys about what's going on in terms of research there. So let's dive right into it. I structured the presentation roughly in ascending order of the computing hierarchy. So starting at the lowest level of devices, going all the way up to fluffy things like software and how to secure that kind of stuff. All right, so let's start at the bottom. The first lab that I'm going to talk about is Professor Joshi's lab. Professor Joshi's lab on integrated circuits and systems basically deals with the lowest levels of the computing abstraction. So he looks at things that play in the devices domain, how devices interconnect with circuits, and all the way up to basically the things that we know as computing architectures, right? So if you know that an Intel CPU is something different than an ARM CPU, so your laptop is different than your mobile phone, that's basically where Professor Joshi stops. That's the highest level of his abstraction. And at the very bottom, you shouldn't ask me because my stuff is like somewhere in the clouds. We'll get to that later. So nonetheless, there is interesting projects and research going on there. And so maybe just to taunt my own horn a little bit, at the boundary, at the architecture boundary between architecture and software, we currently have a shared project going on, Professor Joshi and myself, where we're basically investigating how we can leverage architectures and modify architectures to support better security primitives. You will see towards the end that what I do is security. So if the entire presentation has a flavor of security, that's my fault. You have to subtract the security from most of the other research that is going on here. All right. The next lab that I'm talking about is Professor Kinsey's lab. Professor Kinsey is very much concerned about all aspects of computer architecture. So again, that is very PowerPoint online recording stopped. What do I do? Retry? All right. That's what computer engineers do, right? The computer doesn't work, you turn it off, you turn it back on, and then it works. And no, just because I do security doesn't mean I just hacked this machine. It's not. All right, so Professor Kinsey is working on all aspects that are computer architecture. So again, there's a little bit of overlap with what Professor Joshi is doing. And so specifically, Professor Kinsey is looking into aspects of secure architectures, high performance architectures. So what can we do? How can we structure architectures themselves to make them more performant? Because depending on the kinds of things, the kinds of computations that you want to perform, additional performance might actually help. Earlier on, we heard about fluid dynamic simulations, right? Tons of computation goes into that stuff. If someone, by designing a better architecture, can make systems that perform those computations much more efficiently, that's definitely a benefit to everyone, even beyond the realm of computer engineering itself. Also, Professor Kinsey plays in the realm of embedded cyber-physical architectures, and so cyber-physical systems in general is a big up-and-coming trend in computer engineering and beyond. So this also plays into fields like robotics, because it turns out that if we have computers that control what's going on in our environment, in the physical environment, then there is very interesting properties, let's say, that these systems hopefully would abide by, and we'll see about this a little later on too. All right, now my keys died. Okay, let's use the mouse button instead. Moving on to the CIDR lab, the lab of Professor Densmore. This is very exciting research that is going on there. So many of you know that you can program a computer. You write software in various programming languages, and then you have some sort of chip that is actually calculating those programs. It turns out that you can take biological cells and make them into equivalents of those chips. So you basically can calculate programs on top of these cells. Why is that cool? Well, for example, if you have a diagnostic, right? You want to know, is a certain substance present in this biological tissue, right? You can write a program that makes your analytics light up green, for example, if a certain property is fit, right? And that allows to do all kinds of awesome things where basically biology needs to interact with what we commonly have in the computer engineering realm. And so furthermore, what Professor Densmore does in his lab is basically combining all those things with aspects of design automation. So instead of sitting there and doing everything manually, coming up with automated mechanisms that actually make these things scale. And one of the most awesome products that I've seen out of his lab is basically a programming language. They give you real language that you can then feed into a machine that will fabricate those substances for you. So it's real front-to-end computer engineering that's going on here. All right, moving on to Professor Herbert's lab. What's going on in Professor Herbert's lab can be characterized in only a couple of sentences, if I want to be so bold. Of course, there's many more things that are going on there. But one of the aspects that Professor Herbert is interested in is how can we use FPGAs to improve the life of computer engineers for one and regular people for the other. And so again, you might wonder, well, FPGAs, never heard of this. What are those things? These are basically architectural components that you can program. So instead of having a fixed architecture CPU, you can instantiate logic within an FPGA that can execute oftentimes significantly faster than what a CPU would do. Why is that interesting? So let me give you a very concrete example. If you, for example, go to your favorite online search engine and you type in a term, right? It's a very simple process conceptually that is happening. The search engine will go to a large database, a large index, where it knows all the websites that have all the terms on them, and so it will find the websites that contain the terms that you punched in. If you search for a car, for example, it's very likely that you get millions and millions of hits, right? All right, so it's easy to retrieve those millions of documents, know where they are. The hard part is in actually sorting the results in a way that is meaningful to you, right? And to do those computations, to efficiently sort and rank those results so that they are applicable and meaningful to you is, again, computationally very, very sensitive and very intensive. And so what we can do with FPGAs is basically have dedicated implementations that allow to those ranking algorithms to run significantly faster than if you just took an entire rack of computers. Right? Again, saving for power, for energy, for time, because all of a sudden we get our search results instantaneously instead of having to wait for them for a minute. So making everyone's life better. All right. One of the big aspects one of the big positive sides of FPGAs is that they work more performance efficient or more energy efficient than regular computing systems. And so since we're talking about energy, we have to talk about what's going on in the PEAK lab of Professor Ayşe Coşkun. A big aspect of her research is investigating energy efficiency of different systems, or various systems, I should say. And that ranges from all the things like your little mobile phone, how can we make systems where the battery basically runs longer, all the way to those huge computing clusters, high-performance computing clusters that you see down there, right? There's big savings if you can optimize the energy use of a data center. There's big monetary savings in there for the data center operator. So energy definitely, or energy efficiency definitely one of the core tenets in the PEAK lab. Other interests of research in the PEAK lab are new architectures, specifically those that are stacked, or 3D stacked. So instead of simply having one layer of fabric that allows you to do computation and storage, 3D stacked architectures allow to interconnect those layers on top of each other, therefore shortening the distance for signals to travel, and therefore, again, increasing performance and throughput. All right, which brings us to, since we've already been talking about big computers, what is a big computer? Well, the cloud is a big computer. And Boston University is one of the few locations where we can proudly say we have our own cloud. Right? Many universities have clusters, have research clusters, have big labs with lots of computers in there, but we have our own cloud. And I say own, it's led by BU, but the cloud actually, or our instance is contributed to by all the university in the Boston area, so that includes Harvard, MIT, Northeastern, UMass Boston, and is led by Professor Oren Krieger, and it runs under the name MOC, the Massachusetts Open Cloud. The MOC is awesome because it is from the ground up designed to be an open system. So if you have anything that you want to do with the cloud, instead of simply using the cloud, then the MOC is the place that you should go to. You can do awesome research there. You get access to resources that you don't get anywhere else, right? Amazon will never let you look at their data centers. You go to Microsoft, they will never give you the log information that you would like to have to perform awesome and novel research on real cloud workloads. And so another thing that is absolutely great that came out of this is that, anyone heard of Red Hat, the computer company? All right, good. So it turns out multi-million-dollar company, and they started their first research collaboration with Boston University. So Red Hat Labs has now a foothold here at Boston University. They're investing money in the university. They're investing money into our students. So if you're on the lookout for scholarships, there is the Red Hat scholarship that your potential advisor can apply to maybe get some funding for you from that aspect. All right, Professor Little's lab is looking at all things combined to light, right? So instead of just making the room bright and enable us all to see each other, what Professor Little is investigating, among other things, is whether we can use the lighting itself to communicate or to transmit data. right? So instead of, or in addition to using Wi-Fi to stream data to your phone or to your laptop, maybe we can use the lighting within a room to actually go and transmit information through that way. Definitely very exciting research too. Professor Trachtenberg has a variety of research interests that largely revolve around things in security. And so the material that he sent me basically revolves around mobile phone security. And so as you can see, he is basically interested in anything that makes up a mobile phone, from the GPS receiving chip to the baseband processor to the apps that run on a mobile phone to the sensors that the phone have, right? Not just the GPS sensor, but gyro sensors, compass, and so on and so forth. All the way down to actually the legal aspects that guard what our authorities can and cannot do with phones. Of course, it turns out that the bad guys don't necessarily abide by the legal aspects, but, well, that's where we stand here. All right. So then we have the Dependable Computing Lab from Professor Lee. And Professor Lee, basically, his mission statement is that he wants to make intelligent systems safe, reliable, and secure. So you might have heard that there is a couple of computer industry bigwigs along the line of Elon Musk and so on and so forth. They're super concerned about what AI will do or what intelligent systems will do once they become very powerful and maybe eventually outsmart the people who create them, right? And so Professor Lee is playing in this space, trying to ascertain that the systems that we build are actually safe and reliable to use, right? And that stretches into various areas, including verification of human-in-the-loop controllers, so where it's not a completely autonomous machine controlling things, but there's actually a human providing input to it, artificial intelligence, and so on and so forth. All right, Professor Starobinsky's research, also very broad, and so 3 of the highlights of his research thrusts are, for one, IoT and automotive security, right? So more and more components in a car are actually computerized, to the extent that now we have cars that seemingly drive themselves. We also have cars that are seemingly driven by someone else over the internet if they manage to break into that car and basically hack it. So unfortunately, that happened too. And so this is also where there's this nice interplay with the research that Professor Lee is actually conducting. The IoT, just in case this is not familiar to every one of you, IoT stands for the Internet of Things, also often paraphrased as the Internet of Targets. We will see in a minute why that is the case. But that's basically all the things that look like computers, or that don't look like computers, but at the end of the day are computers. We'll see many more examples of this in a little bit. Professor Starobinsky is also interested in blockchain and cryptocurrencies. Anyone heard of Bitcoin? Anyone bought Bitcoin low and sold it high? If you did, that's good. All right. Furthermore, Professor Starobinsky also looks into software-defined radios. So there's a lot of communication that happens wirelessly, and if you want to do interesting research, there is basically no way to get around software-defined radio research nowadays. So there's really interesting research that is coming out of Professor Starobinsky's lab also in that direction. Oops, yeah, so that's the picture. All right, which brings me to the Secure Systems Lab. That's my lab, and my picture should, I guess, appear at the end of the slide. So I have, very similarly to the other faculty in computer engineering, rather broad research interests. However, I have this combining theme over all of them, and that is security, and specifically software security. So anything that runs software, I postulate has vulnerabilities, and therefore it is a worthy research target for me. So what are some of the things that I looked at, and what are some of the things that get me up in the morning? So we already talked about the IoT, right? Basically at the top left, you can see here all of the things that don't look like computers, but at the end of the day are computers. There is microchips in there, there is software running in there, and it turns out they're all vulnerable, right? Why is that important? Well, as we see in the second quadrant, is that 500,000 or so of those IoT devices have been compromised a little more than a year ago, and been taken to do a fairly stupid job. those devices were commandeered to just send chunk traffic to a victim host, right? If you have 500,000, let's say, home internet routers, they can generate a lot of junk traffic. So what was that victim host? It was one of the most important pieces of infrastructure in the internet. It was a DNS server by the DIN company. And so that had the effect that here on the eastern seaboard in, when was it? In September. Basically for half a day, the internet was gone for all intents and purposes, right? Because no one could resolve DNS names anymore. You cannot get to Netflix, Twitter, Airbnb, all that stuff was gone. It was only for 6 hours. Nonetheless, that's sufficient disruption for what probably amounted like a 2-day job to actually create the worm that caused this outage, right? So if you put a little bit more emphasis and effort into this, you can cause much, much more havoc. All right, where do we see similar numbers than the billions of IoT devices that are out there? Mobile applications. Everyone has a mobile phone, and every mobile phone runs dozens of mobile applications, right? Because there are so many of those mobile applications, we have to ask ourselves, well, are all of those applications secure? And again, the answer is, of course not. The question is rather, how insecure are they? And so similar, that is a very broad research thrust of mine. And then finally, one thing that I like to show to basically demonstrate breadth, because it's a very non-technical topic, is if you take an attacker, a hacker, I don't know, a 400-pound guy sitting in the basement on the bed, or what was the story? And the person steals a number of credit card numbers, right? Credit card numbers are not money. What they want is money. So how do they make money out of credit card numbers? Any ideas? They buy things, yes. So it turns out, if you buy things online and if you sit, let's say, in Eastern Europe, Apple and Amazon won't ship there, right? For specifically these reasons, as in there is many people there with credit card numbers that are not really theirs, and so they don't ship there. What they do instead is they post listings on Craigslist and other job sites to advertise for work-at-home opportunities for people living in the United States. And so what the bad guys do then is they buy stuff online, they have it shipped to those mules, reshipping mules, who then get instructions to whatever you get sent, just put it in a different package and send it off to Eastern Europe. It arrives in Eastern Europe, it gets filtered out, gets sold for money, and then they have cash, right? So very non-technical, nonetheless, very much a global phenomenon, causing billions of dollars in damages every year. And so you might say, well, these are all fun and game stories, but who actually cares? Well, for example, the Navy is funding our projects that are going on in the IoT space. In terms of the mobile application analysis, we actually went out, demonstrated our tools to the US Air Force, because it turns out that their fighter jet pilots no longer carry paper flight manuals, but rather iPads around, right? So they have a vested interest to try to understand what the applications on their iPads are doing. And so when we were investigating the credit card scams that were going on, we were actually working together with the FBI. And so that is the only paper that so far I have written, and I don't know whether there's going to be many more, where I have a co-author with the affiliation of the Federal Bureau of Investigation on it. I guess not everyone can say that. All right. So that's pretty much that. I have one more slide to try to impress upon you why I believe that it is that cybersecurity is so important. Because if you turn back time only a little bit and you look at the presidential debates, there was not a lot of topics where both sides actually did agree. And it turns out one of the topics that they did agree was the importance on cybersecurity. Now, whether you like the outcome of this, I don't know, but they were both right at that point. All right. That's what I have. I have no idea how I did with timing. I don't know whether we have questions. Do we? Do we have time for questions?
Are there any questions? I know there are a lot of computer engineers here.
No questions? Well, many of you have meetings set up one-on-one with many of the CE faculty, not just with me. So specifically, if you don't just talk to me, talk to the other CE faculty about all the things that I couldn't talk about during my brief presentation here. All right?
Okay. Thanks, Manuel. Okay, so next up we have Professor Yannis Paskalidis, who is going to talk to you about the information and data sciences area. Let's see. See if you can find yours. That's the one, right? Okay.
All right. Okay, good morning. I'm Yannis Paskalidis, and I'm a faculty here in ECE, and I also happen to be the director of a research center that we have, the Center for Information and Systems Engineering. So what I thought I will do today is I'll give you an overview of research activities within the information and data sciences group here in the ECE department. But also at the same time, I will give you a broader perspective about this area of research at Boston University, which in fact intersects quite a bit with the activities within this center, SAIS, as we call it. So the center specifically is a home for faculty and students that are speaking very similar, common, I would call it technical language, used in the modeling, analysis, and control of complex systems. And they are, to give you a sense of the size of this community, there are about 43 faculty members that are affiliated with the center. I would say that about maybe 15 or so of this faculty are from the ECE department. And the areas of research that are also areas of research of the IDS group within ECE involve automation, robotics, and control, a lot of activity in networks, and some of that Manuel covered in his presentation, work on cyber-physical systems. So Professor Lee, that Manuel talked about, works in this area. We have people that work in computational biology and medicine, and information sciences broadly defined, data science, data analytics, and also people that work in energy systems, and specifically the new generation of research in energy systems and smart grid issues of demand response. In general, these are some of the methodologies that faculty in this area apply to different problems. So you will see things that range from areas that are more specific to electrical engineering, like signal processing, for instance, and information theory, and computer vision, and computer science, computer engineering, to areas of research that are perhaps closer or intersect with other disciplines in applied mathematics, operations research, including applied probability, statistics, stochastic processes, multi-agent systems, machine learning, and some of the problems that people are working on, especially these days, and I selected a set of problems where I think there's a broader societal interest in these types of problems. So one relatively large area of research has to do with smart cities. One of the objectives is to study transportation networks, to study autonomous vehicles, with the goal of making a city much more efficient and smarter, reducing congestion, measuring the environmental impact of congestion, and coming up with ways of, in fact, better organizing the transportation network, but also the set of services that the city offers to its citizens so that one can make the city operate in a more efficient, in a more smooth way, and a more environmentally friendly way. Another area of research is in improving public health, and you may ask, okay, what is the connection between public health and electrical engineering? So it turns out that we developed quite a bit of techniques in machine learning and data science, and public health and health in general is an area where there is a revolution, I would call it, going on. There is much more use of data. These days, there is a lot of digital data that are available, from electronic health records to various sensors that we all carry with on an everyday basis, from smart watches to smartphones that now have a lot of information about our health. And therefore, there is a tremendous opportunity to use data science and machine learning techniques in order to infer, to predict, and potentially attempt to prevent and alter behavior. So that's, I think, an emerging and relatively important area of research. Cybersecurity, I will not get into a lot of the details because Manuel covered this topic. Another area where people in the IDS group work is on impacting homeland security. So using techniques that have traditionally been generated, being popularized within the signal processing community, looking at image processing, looking at video processing, looking at processing signals that one can obtain from sophisticated machines like scanners that scan bags for explosives in the airports, and then developing algorithms, developing computational methods in order to detect threats. So anomaly detection, detection of specific substances or specific compounds that are in luggage or in passengers is the goal of this type of research. Another area that I mentioned briefly earlier is working with the electricity systems, not so much on the generation side, much more on the distribution side, thinking about how to better organize the grid so that one can afford a much larger percentage of renewable production. One of the issues with renewable production is that there is a lot of variability. So wind is not there 24 hours a day, the sun is not there 24 hours a day, and this creates issues because you cannot store very large amounts of electricity. You have to meet the demand, otherwise there would be a blackout. So you need ways that facilitate the matching of demand and supply. And one of the common ways that now people are doing a lot of work is on demand response. So rather than keeping production facilities that are not operational and are on standby and are ready to kick in whenever there is more demand, make the demand itself to reduce the consumption whenever there is not enough supply of electricity. And in fact, the cloud and large data centers are one opportunity where one can reduce their consumption at times when that is needed. And that is actually a topic where people in ECE department here are doing work. Aisha Koskun, for instance, is doing work in this area. And finally, so I have a broader category of revolutionizing communication systems, imaging and sensing technologies that are technologies that enable research in all of these areas that I've mentioned. I'll give you very quickly a snapshot of some actual specific projects that either are currently being active and or they very recently ended, so to get an overview essentially of the portfolio of research in this area. And I'll skip things that have been mentioned earlier. So I would mention, for instance, this project on algorithmic approaches to personalized healthcare that I happen to be involved with. This is a collaboration with one of the hospitals in the area, the Boston Medical Center, the Boston Medical Center is the hospital that is affiliated with the BU School of Medicine. And we have, in my group, in fact, access to all of their electronic health records. And we are doing work on predicting hospitalizations from chronic diseases and offering decision support tools to physicians so that they can prevent these types of hospitalizations. So you can see here on the right bottom corner of the slide, this relatively large center of research that is being funded by the Department of Homeland Security. Professor Karl, who is the chair of the ECE department, Professor Castanon, Professor Saligrama are involved in this activity, and they develop these video analytics techniques and also these techniques that process signals from scanners in airports in order to detect threats in an airport environment. Some additional work I would mention. There is work, for instance, that involves cyber-physical system techniques, control system techniques applied to multi-agent systems, so to systems of many robots that, for instance, think of a fleet of quadrotors that may fly in an area that is fairly congested, either in a downtown urban area or in a remote area, but within a forest where there are many obstacles. And there are questions of how these vehicles will cooperate in order to achieve a certain mission. And in one of the projects, this was in fact a 7-year effort that was funded by ONR. ONR is the Office of Naval Research. We collaborated with a large group of biologists that were actually studying animals, how they fly in these very complex terrains like bats or birds, and trying to learn from what they do in order to program and develop strategies to better navigate and complete missions in complex missions in these areas. Let me also mention this project Scope, a smart city cloud-based platform and ecosystem, where some of our faculty are involved with this activity. And this, in fact, is trying to take the idea of an open system and an open cloud that Professor Aguilar talked about to the smart city setting. So if you think about a city, you can think of a city as a system where different vendors, different services come in and plug into the infrastructure of the city. And most of the times, these are proprietary systems that do not talk to one another. And the whole idea is how you can create an open system where there would be proper specifications, and then a vendor can come in with a solution, with a software solution or with a hardware solution, and plug into this ecosystem in a way that, for instance, sensing information from that, the equipment of that vendor can be used by someone else that develops a different service within the smart city. So how much more time do I have? Okay. So I put together a slide which in fact is motivated by some of my work in this area, and actually some of the work of some other people within IDS. And I picked an example. So this example is from healthcare. But I think the questions that, and you can see the questions and the topics in these boxes, in fact apply to many different systems. So you can think of answering and addressing the same questions in a smart city context. You can think about answering and addressing the same questions in a communication network context or in a sensor network context. So we are essentially developing methodologies that are broad and general and can predict So this is machine learning, this is data science, developing predictive models that can control, that can regulate, that optimize. So these use ideas from control systems, use ideas from optimization that can diagnose. So this is detection that is very common theme in signal processing. It is anomaly detection in some instances. It is detection of specific signals that come from imaging, that come from different sensor modalities. Sometimes you want to combine different sensor modalities in order to facilitate detection. And eventually you want to also learn, use information that becomes available to you and learn. There is a notion of what people call active learning. So many times it is expensive to acquire this information using different sensors. So one of the problems that people think about is, okay, how to decide whether the information that you have is enough to make a decision or you need to acquire more information. And this interplay between deciding what resources you need while you are learning is in the area of so-called active learning. So these are some of the activities that we are organizing within the center. Some of these activities are in fact organized with a lot of ECE faculty, and I think the purpose of this slide is to give you a sense of the overall student community that we are trying to build. So we have been organizing events. So for instance, in January, we ran a workshop which was a student-organized workshop. So it was like a regular conference. There was a call for abstracts. There was a program committee. There were chairs of this workshop, and students submitted abstracts of their work. They were reviewed. They were evaluated. Some abstracts were selected for a presentation. And then for a full day, from the morning until the early afternoon, there were talks, again by the students, about their research. And part of the objective is to essentially create this community, understand what each one is doing, so that we can facilitate interactions. But also at the same time, it's a great opportunity to hone in your presentation skills, so that when you go to a conference, when you go to a job interview later on, you are more experienced in terms of giving a talk. We are organizing events with industry. There is a lot of faculty from other institutions that are visiting to give seminars, some of them on longer stays if they are on sabbatical. So it's a very vibrant, I would say, community of researchers that do work in this area. And this is the people that are mostly affiliated with IDS. So you will see that there is some overlap with other areas of research, more with computer engineering. But this is healthy. People are involved in many different activities, and that's why they appear in different slides and in different places. So that's what I had today. If you have any questions, I'll be happy to answer. Yeah.
So you gave some examples of some projects that were worked with the university and other entities. So I think in an earlier part of the presentation before you, there was an example mentioned about being able to take logs from the mock, whereas you wouldn't be able to get that information if you were working with some kind of proprietary cloud system. And then you gave some examples here of having access to EHRs, or possibly doing research in using drones in an urban environment, both of which are examples of things that are typically very protected or legally not allowed in areas.
Yeah.
So it sounds like kind of with these types of projects, there are provisions put in place to enable research on things that outside of a university context maybe wouldn't be possible. Is that pretty typical for projects throughout the department here?
So I think, so even within the university, some of this data are not available to anybody, right? So there are specific guidelines, and especially with medical data, whoever is involved has to be on an IRB. Even in this case, with the project we have with the hospital, the data are not even here, are not even in university computers. They are in a data warehouse of the hospital, and we have access to a server there. So I think that, especially now that more projects are data-driven, depend on data, my message is that there are such projects, there are opportunities to be involved, and in each case, the student that will be involved will go through the regular process of obtaining access to the data. So that may involve some training, so human subject training in the case of the hospital data, and getting the proper permissions so that one can access the data. But it is possible, right? I mean, if you go to an institution that doesn't have this type of projects, then it's almost impossible to be able to engage in such area of research. Here there are such projects and there are opportunities to be involved.
Thanks.
All right.
Okay.
Thank you.
Thank you, Amit. Okay, so we are nearing the end. I think what we'll do now, I will talk to you a little bit too, but why don't we do a little bit of a stretch, use the bathroom, get more coffee, whichever order you would prefer. And I'll see you back here in 3-4 minutes, okay? And to all of you who are listening online, you can also put in questions. Professor Popovich will look and see if you have any questions, and we'll relay them up so you can also ask questions. Okay, I think we are full house again, so welcome back. And my name is Anna Swan, and I am the grad chair in ECE. And the goal for you who are here and you who are listening for the virtual open house is basically to become more familiar with what's going on here at Boston University and figure out if this is the best home for you for your PhD. It's a big decision. It's going to be the next 4 or 5 years of your life, and it's going to determine a trajectory for the rest of your life. So it's not to be taken lightly. You are here because we think that you will have a great match with us, but obviously that's for you to decide in the end, what works and doesn't work for you. So the schedule is set up to get hopefully as much information as you can in a short time. After this day, it's not over. Obviously, you can contact any of us back again to get more information. And many of you are local too, so you should make use of that and make sure that you find out what you need. And the graduate students that are here, that you're meeting several times today, are a very good resource too to find out, really behind the curtain what's going on, how the sausages are stuffed, so to speak. So the schedule for today, we are almost done with this first part with the presentation from different parts of the department. You're going to soon go on to meet with faculty. Lunch will be with graduate students, some faculty. There are going to be some tours. So one is to the SILSE Center, which even if you are not interested in that per se, I think you should go because it's beautiful. And another is at the Hariri Center, and also lab tours that start here in the Photonics Center, 2 labs in photonics. Oh, I'm sorry. Welcome back. Then again, meeting with more faculty and poster session back here in the 7th floor in the atrium at 3 to 4. And if you want to spend part of that time talking to more faculty, this is for you to use the day as you will get the most out of it, of course. At 4 here, it'll be 4 to 6. There's a entire college has an open house. So this is you're going to meet other potential PhD students that have all been admitted, and we're hoping to see you come. So you'll hear from the dean and meet other students. And dinner tonight. Okay. And tomorrow, is there anybody who's going to the OSA SPIE conference here tomorrow? Okay, Jennifer is. So they are also setting up a few things here. If you want to, I think the registration is all whopping $20 or something like that. It covers food and stuff like that. So if you're interested in the optics space of things, you can think of going to that. So why should you come to BU for your PhD? So I hope that you heard from faculty today that there are a number of really exciting and relevant research opportunities, research that's going on here at BU. And something else that I hope is coming across is that at BU there is really a culture of collaboration and taking your discipline and working with people from other disciplines to make something bigger. And we also really love our location in Boston. It's a very fertile area for ideas. There's so many things going on here. You can easily find out what's going on at other universities. The town, the city is I think is very nice. It's easy to get around, walking, biking, public transportation. You don't need a car. Actually, a car could be a problem. So it's hard to drive in Boston sometimes. Personally, you see the river. I row on the river. Huh? Easy to drive, hard to park. If you're an aggressive driver, it's easy to drive. And the other thing, we are a growing program. We are moving up in the ratings. We are getting more students, more faculty, more money, and good things happening here. So, which is it's fun to be part of something when it's in a growth phase. So, particularly, if you look from the student perspective, we have around 120 ECE students, PhD students, but as you've heard, we are working with other areas too. So ECE faculty is actually supporting around 170 students total. So those students come from other departments. BME stands for biomedical, MSc material science, ME is mechanical, SC is systems, CS is computer science, physics, chemistry, and astronomy. So that's, I might have forgotten some, but these are where the main students come that we are working with. And you see where we are, or where you are right now. It's in the Photonics Center. And so if you look at the incoming graduate students, 2015 we had 18 new students. 2016 we had 38 students coming in. Last year we had a whopping 44. I almost died. It was wonderful, but it's like, whoa. And this year we are targeting 40 new students. And we certainly hope that you will be among those students that are coming, so I can show you next year when we're doing this. And the reason why we are, growing our program is that we need to have you, the graduate students, in order to produce the work that we are getting the funding to do. So that's really students are key to all the interesting research that's going on here. And this is a 10-year snapshot. So you can see that we are growing in our research funding. And other than student, of course, there's the faculty, and you heard a lot about this. So the way it divides up right now, it's we have 10 assistant professors, 10 associate professor, and 31 full professors, with some variation in women and underrepresented minorities. And I think you already heard, but we just last week, or this week, Professor Darnegro was promoted from associate professor to full professor. So these numbers just changed. So this is the new faculty from 2016. That was a great year. Milos, who's right here. And then McKinsey and Wenchao Li in the computer engineering field. Lei Tian, who straddles both information and data sciences and the electrophysics area. And Alex Olszewski, who is in the information and data sciences area. And last year we have 2 senior faculty hires. So Chen Yang, who you heard from Milos, and also Jixin Sheng, who is has a named chair. He's the Theodore Mustakas Professor of Optoelectronics and Photonics. And we also have ongoing searches. So we are looking to hire in these fields. And those of you who are on campus, you can go and hear the talks from these people that are coming for application. You will see them announced. You might have to be a little clever to figure out that it's a faculty applicant, because it doesn't say. But if it's a young person, you're in these areas, so you can be pretty sure they're on our search. And they are not a professor already, yes. Right, so postdoc or PhD student. So this is also very exciting to grow in these areas. The other thing, I think, which is very strong for Boston University, is that it is an interdisciplinary space. Research is very much organized around a topic rather than a department. So this new center, the Silsey Center, which is the newest center that we have, that's on ComAv, it's really organized around this Center for Integrated Life Science and Engineering. That's it. So then you have people from different schools and colleges that work together there. And I can tell you, even if you're not working with somebody, if you're next to somebody from a different department, you will start interacting just because your proximity matters. And Doug Densmore, whose lab is going to be shown later today, is working with 2 BME people, and they're doing all this crazy stuff, programming biology. So that's really, he's taking his core in computer engineering and bringing that skill set over to biology and to do really interesting stuff. So Hariri is another. I'm just highlighting 2 of these centers where you have really broad variety of disciplines that come in, and of course they are interested in computing and computational science. So the BU Data Sciences Day that we just had, Brian Coulis, who is our faculty member, was a co-chair with somebody from sociology. So you can see how that doesn't really seem like that's a natural fit, but it is, because they're both working with data and computer science. So I think the 2 blue ones are highlighted because if you want, you can go there this afternoon. Photonics Center, you heard from Tom Bifano. And then we have divisions in engineering, which is not, they don't hire faculty directly. They have faculty from the departments, but they organize around topics. So one is around materials and the other is systems. And that's where you heard from Yannis Paskalidis, the center he also highlighted is size. You heard about Open Cloud, Massachusetts Open Cloud, and the Red Hat are part of that. On the provost level, there is a data science initiative. So they're looking to hire faculty in data science because it is a growing and important area. Then there are other centers. I'm part of BU Nano, which is also organizing people interested in nanotechnology. You heard about the new NSF Research Center, and there are many more. So in terms of what you see I already said this a little bit, but you as students can have ECE faculty and work with other groups, or you can have a different faculty member outside of ECE and work with. Even if you're working with somebody in ECE, chances are you will know or work with somebody, a student from a different department in the same topical area, because of the problems that you will be studying requires input from several disciplines. And of course, as a student, you're free to take classes outside of ECE if you want, if that fits what you're interested in. I think what I want to do, I don't actually have the slides for this, but I'm going to stop here a little bit and ask you if you have any questions about what the sort of the first mechanics of the first year, what it looks like. So get back maybe to Jennifer's question before we had. So what do you do when you get here? You are admitted on a scholarship, so that will the first 2 semesters you will not be teaching. You will take classes, and your most important job is to get involved in research. So to find professors that you are interested in and work with. So that's you will sign up for research and either do it with one professor or sample. And I think it's a very good idea to start thinking, if you're coming to BU, start thinking about this now and contact the people that you're interested in working with and find out that this is a good idea, and find out what the matching is. So there's this good good impedance match with your interests and skills and what's required. Then so that first year, you probably, if you're a post-master student, you will take 2 classes, and then basically you will be done with your class requirements. If you're a post-bachelor student, you will take, the first year you'll probably take 4 classes, 2 and 2. Is pretty typical, and the third 4 credits will be research credits, which you will engage in research, maybe not in the sense that you're writing a paper, but you will sample and find out what's going on. That's your most important work during the first year, to figure out your trajectory. Then in the summer, we are expecting you to have figured out who you're going to be working with and start working with that professor, who will then start supporting you on his or her grants. Questions regarding that? Yeah?
If you are postmasters, do you still have that first year without TAing, or
yes.
is TAing optional?
Yes. So some of our students, so your teaching you typically do in year 2, maybe spills over to year 3. Sometimes, especially if you have students who went to BU, have taken all the classes, they might choose to do some of their teaching early, and especially if your background is in computer engineering, we have great needs for the teaching in that area, so that might be spread out a little bit. But typically, teaching happens year 2 and maybe a little bit year 3.
Okay.
Is teaching like a requirement going through the program that you have to teach a certain number of hours? Or?
Yeah. So if you are coming in on a fellowship, ECE fellowship or a Dean's fellowship, you will be teaching 2 courses. And it's part of we see it as part of the academic requirement. If you're coming in funded directly by a professor on an RA, you will also teach, but you will have more freedom in figuring out what courses you will teach. But everybody will teach 2 semesters.
Have you had any PhD students complete a PhD program in 3 years? And if so, what unusual or special concerns would that entail?
Okay, so 3 years is unusual. I think we looked at it, and there are a couple there, maybe 3 or 3 plus 1 semester, or something like that. There are typically post-master students that do that. I really don't think we have had any post-bachelor students that have gotten through in 3 years, because just the coursework is just hard to do.
Yeah, this would be a postmaster student.
Yeah, I mean, really, it's like if you can do the work in 3 years, that's great. We are encouraging that students don't linger. We want a flow through our program, so in terms of what is required for you to be done.
For the credits, it's 2 credits per semester of doing your PhD.
Oh, no,
right?
you don't. It's like if you the research credits, it's kind of funny credits in some ways. Like if you do 2 credits, 4 credits, or 8 credits, you're going to work your butt off regardless, right? Yeah.
If I needed to.
Yes.
If I were trying to do
Yes.
3 years.
Yes.
It's not that's not the issue.
No, it's not an issue. So go for it.
Question about taking classes outside of ECE. I know that some people have tried to take classes outside the College of Engineering and they've run into a few roadblocks, but can you talk a little bit about that process?
Yeah. So typically, I'm not aware of the roadblocks. Maybe we can discuss that. But so if you are, in your case, maybe you would be interested in, I don't know, some
math or physics.
Yes.
Or
okay.
Something.
So as long as it look like it's in your area of study, there are absolutely no questions. If you decide to do something in expressive dancing, maybe somebody will, your advisor might say, I don't think that's time well spent. But I
don't know, exercise is important for your mind.
Yes, it is. So exercise, this is another thing. We have a formidable FitRec, gym. The gym is just unbelievable. And while you're taking full load of classes, you can get the FitRec classes for free. So you should really take advantage of that. Yeah.
Yeah, because I've been doing it as a master's student, and I want to make sure that I can continue.
You can continue doing that. So FitRec classes, once you're starting doing research only, you actually have to start paying for those FitRec classes. But you get a stipend, so you can afford to. Yeah. Other questions?
Going down the line a little bit towards candidacy, is there a general track for your prelims, how that's done here?
Okay, very good question.
Okay.
So a numbers of years back, we had a more traditional thing where everybody took a test, but we did away with that. So what we are saying is if you do well in our classes, we don't need to test you again. So that part is done by something we call the technical preparation criteria. The short is TPC. if you get here, you'll hear TPC and RPC. So for what that means for master students is that you need to have 2 ECE classes with a grade point average of 3.7. Let's say, and then for the post-bachelor students, within the first 3 semesters, you need to have 4 classes, ECE classes, with a grade point average of 3.7. If you're looking, it's 3.7, not 3.70. So you can look at the variation of grades you can have to do that. So I think that is typically not a problem at all. The students that come in here, are good academically. So it's rare that we see a problem on that side. The other side is the sort of on the research side. You're here to be a PhD student. That's not, the classes are good, but that's not why you're here. It's research. So that's so this first year students now are starting, they have picked a paper to study, and they will present on that paper to a panel of 3 members in May. And then they'll be asked questions, to see that, they have, grasped something from this paper. They know something of the background. They understand the general science of the topic they picked. So if you're a master student, you will qualify, postmaster, you'll qualify at the end of the spring year. And then for a post-bachelor, you have the option of qualifying then or waiting till the January the following year. Yeah. The next step in this is prospectus, which you need to do within 2 years of qualifying. And after that is your graduation, your defense. Okay, so some of you might have, if you have, does anyone have a 11:15 appointment? Okay, release you then. So, and if you don't, you can, I'll stay here and I'll make sure that I can answer questions from people in the rest of the world. And if you have more questions that are not having an appointment, please stay. And we will post this, the video from this will be posted. So even if you have to leave, you'll at least hear the questions and answers that were posted. Okay. Oh, thank you. Thank you. So let's see. I'm going to check on the... Microphone. Can you grab the microphone too?
So my other question is, before today, we were looking at different professors' websites, finding their areas of interest and choosing ones that we think might align with us.
Yes.
And then today we're learning more about what some of the more current things are.
Yes.
How would you recommend continuing to explore different professors that we
I think what you can do after today, if you don't have time to do that today, contact the professor you're interested in, set up a Skype meeting, or, depending on how far away or local you are, come back in and see us. But telephone, email, Skype, that all works really well.
Okay.
Yeah.
And that's also just a continuing thing throughout the first year, or is this something that you really ought to be started before the first year?
I think it's nice if you start it before the first year, because when you come here, there are other things hitting you. You know, you have to find housing, you have to do your classes. So if you have thought about this beforehand, I'd say it's much smoother and easier for everybody.
Okay.
Yeah.
Thanks.
Just going to ask, the oral presentations, which are part of
yes.
passing criteria, are those public, or could we potentially listen into one of them this spring?
Oh, that's interesting. Actually, no, we have never done that. It's a closed session thing with a student and 3 professors. But what you can do is you can go and talk to students that went through it and find out. I mean, that's what we are doing this year. The second year students are talking to the first year students about what their experiences were, what some pitfalls were. I mean, you are going to be grilled. It doesn't mean that you are going to fail. It's like this is part of, the professor want to find how far your knowledge stretches and how you think,
so
basically.
That still hasn't happened for this year?
No, so that happens in May.
In May.
After classes are over.
Okay.
Yeah.
Sounds good. Thank
you. Okay. So I got a question from Anil. What kind of computer facilities are provided to the PhD students for their experiments? Dedicated services. Now, I'm not the right person to answer specific computer. It's like every student will have access to a computer. If you need clusters and stuff like that, there are computational clusters that you can get free of charge. I know my students are using some, and I'm not in any computer engineering aspects. So whatever you need will be provided, unless you have very special needs that I'm not aware of, but I think that should be fine. Thanks for that question. I see Zahid is typing a message. We'll see what that is about. Daniel, do you have a question?
Just to add on to that also, one of the things that was mentioned in this morning's presentations was the idea of the mock project that's been worked on.
Yes.
And I had read on the mock's website that they make cloud computing resources freely available to Boston University students.
Yes, exactly. And if you talk to Professor Oren Krieger, he can tell you a lot more about that. And he has been instrumental in getting Red Hat to BU, and they are also trying to figure out how to best spread money around to students. So there'll be also financial opportunities if you're interested in that space of cloud computing. Yeah. It's good to have your own money rather than your professor's money for everybody. But yeah. Let's see. Can we be part of multiple groups? Very often a student will have a co-advisor. So maybe that's what you're referring to. So you will work with one professor and maybe be paid by that professor, but you will have group meetings and projects in common with other groups. So that happens, and if that's your question, it's yes. Okay. We're waiting for a question from Novak. Maybe. Let's see, can I show this on the screen? I don't know. James, how can I put up the view, the conversation view to the side here? Sorry. Okay. Escape here? Oh, sorry. I'm on the wrong one. Yes. Okay. Okay. Thanks. Okay. So how does the process of choosing advisor look like? Very good question. So this is really key to what you will be doing first and most importantly when you get here. I think what you should do is to look at research that's going on at BU, preferably even before you come here. Contact professors to find out if they are hiring, how many students they are hiring, and professors can be a little bit cagey about that because you put in proposals, but you don't know exactly if they will hit or not. But they will have some idea if they're looking for students or not. And then talk to professors, talk to students, figure out what kind of research they are doing. Are you interested? Do you have the background needed, or can you pick up on the background needed? We have electrical engineer that decides they really want to go into computer engineering, and it can work if everybody is well aligned and put the work in, but that makes everything much harder because you don't have all the background that you might need. So figuring out that's also your job right now, is figuring out are there enough faculty? I think you would say that you need to at least 2 or 3 faculty that you would be happy working with, because we are dealing with the statistics of small numbers. So if there are 4 people that want to work with Milos and he's only hiring 3, then you might be out of luck. So you need to think a little bit about that there's enough breadth to what you are interested here in the department. Novak, did it answer your question? Or we also have in the fall we have seminars by faculty and ways to find out more about what's going on. But a lot of it is legwork by the student to go around and talk to people. You will also be contacted probably by faculty, and please answer and say yes, I'm interested, or I'm not interested. But it's nice to get an answer. Okay, so looking for Anil. Does it happen that after the first year a student did not get an advisor? Yes, not typically. And if that student is... So typically what can happen is that a student matched late with an advisor, and the advisor wants to have a chance to evaluate if this is going to work. So if this looks promising, we can extend this period of trial period, and the department can step in. But if a student hasn't not made any inroads to working with somebody after a year, I think then this is not the right way. And if it's a post-bachelor student that hopefully ends in a master's, and if the master students, it's just something that gets finished. But I would say that's rare. Our students do find advisors. And if not in the ECE department, in a nearby department for computer science, if it's computer engineering, physics, or mechanical maybe. If you're interested in optics, there are a lot of people in different areas. Okay, good. So are you done? Yeah, okay, good.
So I heard that depending on field, so in this case like ECE, but also depending on university, different researching groups tend to work more heavily at targeting conference publications or journal publications. Yes. What would you kind of describe as the case here?
Okay, so for computer engineering, conference publications that's the important stuff. That's what gets valued. That's what peer reviewed. That's where you show yourself. In my field, which is electrophysics, conference publication doesn't count for anything. In electrophysics, you publish in papers. That's what counts. So it's very area dependent. So what you will publish in the area that is important in your field so that you get seen. That's the way it gets done. Yeah. Okay. Any more questions from abroad? Okay. If not, I think we will end this part of Oh, okay. Yes. So does it mean that the advisor doesn't have to be from ECE? So we have, if it's a, for example, let's say it's a physics advisor, we have several physics professors that has affiliated in appointment in ECE, and then they can have a student without any other ECE faculty. If you're working with somebody that does not have a ECE affiliation, you will also have to find an ECE professor to be part of the whole thing as a co-advisor, and that could be at least minimum once a year. You need to sit down with your co-advisor so they can figure out what's going on and that you're doing things that fits in the ECE space. So yes, you can have an advisor outside of ECE, but we do want to make sure that we don't lose the ECE affiliation. Did that answer your question? Okay, good. Thanks. Obviously, I'm available via email after this virtual open house session if you have more questions. And I can, these presentations will be posted. You'll be able to look at them again. The tape of recording of this session will also be posted. Okay. Okay, with that, I think that's a good time to close this session. Thank you, everyone. Thanks.